Now that we know what inverse equations are, we have to learn how to come up with them ourselves. So if we have an original function and we need the inverse function of it, we need to be able to use some reasoning from yesterday and also some algebra. So on the basis of what we did yesterday, put a little bit of thought into how you think that we can change this equation here into an inverse equation, remembering that the f of x just represents with a y. So yesterday in our inverse, we realized that you just make your x your y value and your y your x values. So that's all we have to do here. So let's start by doing that. So if our original equation is y equals 2x plus 1, and we want to make an inverse equation, just remember to make your output your input, and your input your output. So now I have an equation that will read x equals 2y plus 1. I just switch places with the x and y. Now a little bit of algebra, and the equation is done. X minus 1 equals 2y. Divide both sides by 2, and you have a final inverse equation over here. Remembering that we show it with the negative 1 equals x minus 1 all over 2. There you go. So let's do it again down here with this equation. So I'm going to switch my x and y's to find the inverse equation. So I have x equals 3y plus 5. A little bit of isolation, x minus 5 divided by 3. And that leaves me with the inverse function. Now that I have an inverse function, if it asks me to substitute 2 into it, I have to be sure that I use the right equation, because we have our original function here and our inverse function now. So because it says f at negative 1, I'm going to substitute that 2 into my inverse equation. So I'm going to have 2 minus 5 divided by 3. That gives me negative 3 divided by negative 3, which gives me a final answer of f at negative 1. When x is 2, we know that the y value would be negative 1. This here, negative 3 divided by 3 is negative 1. Okay, so another example, very similar. I have to go into my inverse function with an x value of 5. So I have 5 minus 5 all over 3, which equals 0 divided by 3. And anything with 0 as the numerator gives us a final answer of 0. So inverse at 5 equals 0. Here, be careful with this. Now with this function here, f at 3, we need to remember this is talking about our original function, not our inverse function. So it's important that we substitute back in to the original one. So giving us 9 plus 5. So f at 3 must equal 14. So when I go to look at this question here, I look at the fact that I'm looking for the inverse. I need to know what the inverse solution is when x is 14. Now if I'm looking to make some shortcuts, save some time, I realize here that when x is 3 on my original function, that y is 14. So if I was to find the inverse of that, I would switch places, right? So the inverse would be 14 and 3. So look what it's asking here. It's asking when x is 14 on the inverse equation, what is y? So without having to do any work there, I can tell that my answer is 3. It's helpful to find these tricks to save some time on your test. All right, last example for today is that we have a function g at x, and it wants to know when x is 2, what is y? So everywhere where there is an x, I substitute in that 2. Oops, clean that up, that's supposed to be addition. So 3 times 9 equals 27. So when g is 2, This can also be written as an ordered pair, 2 at 27, keep in mind. So now I have my function g at -1. It wants me to solve for when it's 3. So if I want to save myself some time, I have to just remember that if it's asking for it as x here, on the original function, that must have been when y was equal to 3. So if I don't want to have to do all the work of finding my inverse equation here, I can just sub this into 3 as opposed to x in my original equation. So here what I'm going to do is I'm going to put 3 in here, 3x plus 7, and then I'll be able to come up with the answer as well without having to do the inverse equation. So 3 divided by 3 equals 1, minus 7 equals x. So my answer here must be -6. So it's nice to learn these tricks so that you don't necessarily have to build your equation every time. So same thing here, if I'm looking for a 0, I can just substitute that into the y, 3x plus 7. So I divide both sides by 3, which is still 0, and 0 minus 7 equals -7. There, our final answer, g inverse at 0 would be -7. Here in D, it actually asks for the inverse equation, so if it does, then you actually have to be sure that you take the time and show that work. So we would be left with x equals 3, y plus 7. And then it just takes some isolation. So we have x divided by 3 minus 7 equals y, or represent it with the inverse equation of it. And I think at the beginning we were using g. So let's just keep it consistent that we also still have g there. So that's our inverse equation. So if it's now asking in E, the final question here to find g at -1 when x is 8, we can use this equation being that we already have it. And with this, sometimes we're going to have fractions and we have to deal with it. So we're going to have to do some common denominators here real quick. 8 over 3, which would be 21 over 3, for a final answer -13 over 3. And that can't be reduced, so we're done there. When you get into your practice questions in class tomorrow, keep in mind that you can do this both ways, that you can find the inverse equation or you don't necessarily have to. What I'm going to leave you with at the bottom here is our function f at x equals 3x minus 2 in parts A, B, C, and D for you to try, and we'll talk about them at the beginning of class.